Each video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercises. To master each topic, you must use the module's components together. View the video program, read the manual, and work the exercises.
Welcome to GL 504, the last of our 3 modules on sandstone depositional systems. Well, so far we have looked at the many different continental settings where sandstone is deposited, and we've examined sandstones originating in coastal environments. We now look at the realm of the ocean. Here sand is deposited in 2 distinct environments, on relatively shallow continental shelves and in deeper regimes at the foot of continental slopes, as well as on the slope itself.
Until recently, we haven't been able to examine deep-water depositional processes or the nature of recent deep-sea sediment firsthand. That is, not until the advent of marine research, which began in earnest about 2 decades ago. So it is only now that we are beginning to fully understand these depositional systems and the importance they play in producing reservoirs for major oil and gas accumulations. Let's start with continental shelves. On modern continental shelves, sand originates from land sediments and shallow marine sands that have been transgressed by post-Pleistocene sea level rise. Additional amounts of sand may reach the shelf via rivers or from coastal erosion. 2 basic types of currents are responsible for most sand deposition on continental shelves: tidal currents and storm-generated currents. As we know, tides are twice-daily horizontal water motions generated by the relative gravitational attraction of the moon and, to a lesser degree, the sun. Tidal range and the corresponding velocity of tidal currents may vary around the world, depending on the configuration of the shelf. As we saw in GL 503, coastlines may be classified according to tidal range: microtidal coasts with less than 2 meters tidal range, mesotidal coasts with tidal range between 2 and 4 meters, and macrotidal coasts, where tides exceed 4 meters. On some macrotidal shelves, tidal range may be amplified up to 15 meters, with corresponding tidal currents reaching velocities up to 200 meters per second. Usually, the back-and-forth motion of tidal currents, called the flood and ebb, is of equal duration. However, flood and ebb commonly have different peak speeds. This results in net sediment transport in the direction of the stronger current, in this case, the flood current. These tidal currents interact with the sea floor, causing near-bottom currents to flow parallel to the contours of the shelf floor. Thus, they flow approximately parallel to the shoreline. In this map of the North Sea, we see by the direction of the arrows that sediment transport is parallel to the coastline, being ebb-dominated in some locations and flood-dominated in others. Storm-generated currents are the second major sediment dispersal agent on continental shelves. Like tidal currents, storm-generated currents are deflected by the shelf bottom to flow along bathymetric contours, and thus parallel to the coastline. We see here that off New Jersey and Long Island, on the storm-dominated U.S. Atlantic shelf, the directions of net sediment transport are essentially parallel to the coastline. With an abundant supply of sand, near-bottom currents create 3 types of bed forms. First, flow-transverse bed forms occur as ripples, mega-ripples, and sand waves that form sheets of sand. With increasing current velocity, flow-oblique bed forms develop as large-scale sand ridges. Finally, parallel flow forms occur as thin ribbons of sand, where high-speed currents sweep the sediment over a coarse substrate. The most important sandstone facies of the shelf environment are these large-scale flow-oblique sand ridges. Extensive sheets of sand and gravel occur on several present-day tide-dominated shelves, for example, around the British Isles, as we see here. Grain size within these sand sheets may vary from gravel to fine sand, with sorting usually good to very good. Most known petroleum reservoirs and ancient shelf sandstones have been interpreted as sand ridge deposits. Modern shelf sand ridges occur in the southern North Sea as the result of tidal flow. On the Atlantic shelf of the eastern United States, ridges result mostly from storm flows. Sand ridges often form on the surface of an underlying, more widespread sheet of finer-grained sand. The ridges are oriented at an oblique angle to current flow, and thus are also oriented generally oblique to the shoreline. They may align themselves either clockwise, as shown here, or anti-clockwise with respect to current direction. Here we see the oblique trend of the southern North Sea sand ridges with respect to net sand transport and the shoreline. Note the anti-clockwise offset of these ridges. The storm-built sand ridges along the U.S. Atlantic, however, generally display an oblique clockwise orientation with respect to the direction of sediment transport. Modern sand ridges, whether built by storm or tidal currents, tend to be asymmetrical, with the steeper flank on the down current side. However, as we shall see later, this relationship is apparently reversed on some ancient shelves, where the steeper flank is on the up current side. When ridges are formed in a parallel series, the distance between crests may vary from 1 kilometer to 5 kilometers. Large individual ridges may reach sizes of 50 kilometers by 30 kilometers and obtain a thickness of 40 meters. Ridge slopes are low, with a gentle flank commonly less than 1 degree, and the steep down-current flank less than 7 degrees.
Modern sand ridges vary widely in texture, depending on the nature of the available material, as well as on the strength of the transporting water currents. Let's now examine some of the criteria for the recognition of shelf sands.
These sketches, based on reflection seismic profiles across modern North Sea tidal ridges, show internal interfaces dipping approximately parallel to the steeper down-current slope of the sandbank. The reflections are probably due to the acoustical impedance generated by thin layers of soft mud that define the gentle dips of master bedding surfaces. These mud partings are apparently deposited during periods of slack water. A type of stratification called hummocky cross-stratification is characterized by laminations of fine to very fine sandstone in the form of alternating hummocks and swales. This type of stratification occurs on the shelf at depths between fair-weather wave base and storm wave base, and is generally believed to form in storm regimes. Thus, many geologists use the presence of hummocky cross-stratification to differentiate storm-built shelf deposits from tidal shelf deposits. Fossil assemblages in fine-grained rocks associated with shelf sandstones should indicate deposition in a marine shelf environment. Trace fossils in the form of horizontal and vertical burrows are common in the mudstones that underlie and overlie shelf sands. Burrowing may also occur in the finer-grained sand and silt units of the sand body itself. Shells may be abundant in lag strata and hard grounds at the base of shelf sands. This shell hash tends to occur in zones of higher current velocity in both tidal and storm regimes. Facies associated with sand bodies deposited on the middle and outer shelf are almost always marine shales. Such shales usually surround the shelf sand body and act as stratigraphic seals for petroleum accumulations. Now, let's look at the seismic expression of shelf sands. This seismic model was developed for the Cardium Formation, a Cretaceous shelf sand of Alberta, Canada, that forms stratigraphic traps in long, narrow sand bodies. These thin sand units are only about 3 meters thick and coarsen upward from a shale base to a conglomeratic top that is abruptly overlain by marine shale. Laterally, these bodies are fringed with tight silt that grades into marine shale. The seismic model reflects these overall lithologic changes by showing a strong event at the upper sharp contact and a lower amplitude event at the gradational base of the sand body. As the reservoir becomes transitional into silt, up-dip to the right, there is a gradual decrease in amplitude, and the exact boundary between porous reservoir rock and tight silt is difficult to determine seismically. SP and gamma-ray log profiles of shelf sands may show a variety of shapes that tend to reflect specific flow regimes. In general, the most common of shelf sand log profiles is a funnel-shaped coarsening upward profile, suggesting a storm wave-dominated shelf, as shown on this SP log of the Cretaceous Shannon sandstone of Wyoming. Some storm-emplaced shelf sands, however, may display fining upward log profiles, as we see here from the Cretaceous sub-Clarksville sandstone of Texas, the result of rapid deposition by waning storm currents. A blunt base, blunt top log signature is more characteristic of tidal current sand bodies, as shown by this gamma ray from a North Sea sand body. Cores taken in a shelf sandstone deposit might typically display an upward coarsening lithofacies sequence as illustrated by the productive Cretaceous Viking Formation of Alberta, Canada. The basal facies consists of a burrowed gray shale. This facies is overlain transitionally by a burrowed ripple-bedded sandstone, interbedded with silty shale that is interrupted by a thin bed of pebbly conglomerate. This interval may also consist of a bioturbated shaly fine-grained sandstone. Next in vertical sequence is a trough cross-bedded fine to very coarse-grained, well to moderately sorted sandstone. Shale clasts are common, and the sandstone contains abundant glauconite. Generally, this facies has a sharp lower contact and a gradational upper contact. A pebble conglomerate occasionally forms the top of the sequence. Overlying this sequence may be another interval of bioturbated or rippled sandstone and shale. A similar coarsening upward sequence is revealed by detailed log, core, and outcrop studies of the Shannon Sandstone, a Cretaceous shelf ridge deposit located in the Powder River Basin of Wyoming. The coarsening upward profile often exhibited by shelf sands is similar to the coarsening upward Barrier Island and Delta River mouth bar sand sequences that we saw in GL 503. Therefore, how can we distinguish shelf sands from shoreline sands? First, shelf sands are usually overlain and underlain by marine shale. Second, shelf sands, unless they are attached to the shore face, do not display landward-seaward facies changes as would be expected with a shoreline deposit. Third, shelf sands usually contain abundant glauconite, concentrated in the cross-bedded sandstone facies. Glauconite, we remember, is an authigenic mineral found only in marine sediments. It is extremely susceptible to the subaerial weathering encountered in a beach environment, and its soft grains are usually destroyed by the high-energy conditions of a shoreline setting. Next, shelf sands contain microfossils and associated shales that are indicative of a shelf environment. Finally, shelf sands tend to be isolated from interpreted paleo shorelines. Shelf sands yield sizable reserves in a few fields where they display good porosity and permeability. However, the reservoir quality of shelf sands overall, compared to shoreline sands, is relatively poor. In the cross-bedded sand and conglomerate units at the top of shelf sand sequences, where reservoir quality is best, porosities and permeabilities are generally less than 20% and 100 millidarcies respectively. A major cause for their relatively poor reservoir quality is the high percentage of fine-grained material often found in shelf sands. Currents responsible for shelf sand deposition are periodic, whether storm or tide generated. Therefore, clay deposition can take place during periods of slack water. Also, we have seen that abundant amounts of fine-grained glauconite can be expected to occur in marine shelf sands. Upper Cretaceous shelf sands account for a number of important oil and gas reservoirs in western North America. One of these fields, the Hartsog Draw Field in the Powder River Basin of Wyoming, contains 100 million barrels of recoverable oil. Let's examine this field. The Shannon Sandstone, the main reservoir at the Hartsog Draw Field, was deposited on a broad, muddy shelf that existed along the western margin of a late Cretaceous seaway. The shelf was built on a wedge of sediment that infilled a foreland trough, the sediment having been derived from material eroded off rising thrust sheets to the west. Deposition was at depths of approximately 70 meters and occurred for a distance of 110 kilometers east of the paleo shoreline. Studies have shown that the sand body formed from a series of overlapping sand waves that migrated southward under the influence of storm-induced currents. The sand consists of two main bedding forms, a thin rippled sand sheet and thicker cross-bedded sand ridges oriented at oblique angles to the main current direction. One of these sand ridges comprises the reservoir of the Hartsog Draw Field. The total sand body at Hartsog Draw is about 20 miles long, varying from about 1 to 4 miles in width and reaching a thickness of about 50 feet. Average porosities and permeabilities are about 12% and 12 millidarcies respectively. The clay content of the sand is rather high, averaging about 20%. The Hartsog Draw Field currently has over 180 wells, producing from depths of about 9,500 feet. Initial estimates of oil in place were as high as 350 million barrels, with about 100 million barrels being recoverable. The upward increase in grain size and sorting of the Shannon Sandstone at Hartsog Draw is reflected on all logs, but is particularly evident on the core measured porosity profile. A study based on reservoir quality combined with geologic data showed that the formation could be separated into 5 units of relatively discrete fluid flow characteristics. Units 4 and 5 have the best overall reservoir quality. This lens represents the highest energy of deposition that influenced bar buildup. Clay content and water saturations are therefore at a minimum in this interval. Cumulative production in the field has been highest along its northeastern side. This does not directly coincide with areas of net pay maxima, but rather with zones where flow units 4 and 5 are thickest.
We've seen that shelf sands occur mostly as submarine sand ridges, resulting from storm and tidal currents. These shelf sands can yield considerable hydrocarbon production. However, since both sand and marine clay deposition takes place, and fine-grained glauconite is common, the overall reservoir quality of these sands is often reduced. We know that large deposits of sand and other terrigenous sediment occur below the level of the continental shelf. The ancient analogs of these deep-sea systems have provided significant oil and gas production in many parts of the world, particularly in the North Sea, Southern California, and offshore Brazil. Let's first look briefly at where most of the sediment is deposited, and then at the depositional processes responsible.
At the foot of the continental slope, sediment usually spreads out from the mouth of a submarine canyon in a radiating complex of distributary channels to form a fan-like deposit termed a submarine fan. Coarse-grained sediment may also accumulate in non-fan deposits. These non-fan deposits include slope aprons, as we see here, which are broad bands of sand-rich sediment fed through multiple canyons. Sediment may remain within levied non-coalescing channels that can extend for long distances on the basin floor to accumulate as elongate ribbon bodies of sand. Feeder canyons of submarine fans may also become filled with sand, gravel, or mud to form lenticular bodies of sediment on the slope. Sediment dispersal within these submarine fans and associated non-fan systems is accomplished by several mechanisms, including traction flow, as we see here, and a variety of gravity flows. For most submarine fans and associated systems, sediment influx is high and gravity processes dominate. 5 types of sediment gravity flow are recognized: slides and slumps, debris flow, grain flow, fluidized flow, and turbidity currents. Slides and slumps are coherent masses of sediment that move downslope along external shear planes. Slides like this take place along discrete shear planes subparallel to underlying beds, while slumps occur along concave upshear planes accompanied by rotation or slide. Slides and slumps may retain original sedimentary structures, or they may show deformation in the form of folds or fractures. Mechanisms that appear to trigger these slides and slumps include shocks such as earthquakes, fluctuations in sea level, excess pore pressure in water-saturated fine-grained sediments, and oversteepened slopes. Debris flows are mixtures of granular solids, clay minerals, and water that move sluggishly downslope in response to gravity. Debris flows can be initiated and move along very low-angle slopes and spread out as much as 800 kilometers from their source. Deposition takes place by a process of mass emplacement, and the resulting deposits are of mixed grain sizes, ranging from clay to coarse gravel clasts, essentially a fabric of coarse grains floating in finer material. Grain flow, the next type of sediment transport, takes place by the upward supporting stresses acting on grains within flowing sediments due to grain-to-grain collisions. A typical grain flow in a subaerial setting is represented by sand avalanching down the slip face of an aeolian dune under the influence of gravity. Steep slopes are generally required for the movement of grain flows. Where they occur in submarine canyons, they have been termed rivers of sand. Grain flow deposits are thick and massive, with a fabric consisting of dispersed clasts of pebbles floating in sand. Bed boundaries are sharp, and the base of the beds may include scour markings and lode structures. In fluidized flow, excess pore pressure keeps the sedimentary particles afloat in interstitial fluid. Gravity moves the fluidized sediment downslope, and rapid deposition occurs as pore pressure quickly dissipates from the base upward, a mechanism referred to as freezing upward. Sediment ranging in grain size from clay to sand may be transported by this process. Owing to the rapid upward escape of fluid, Dish structures, water escape pipes, and sand volcanoes are common sedimentary structures in this type of deposit. The base of fluidized flow beds may contain flame and lode structures and possible grooves and striations. Turbidity currents are perhaps the most important type of gravity flow responsible for deep-sea sedimentation. Turbidity currents are a type of density current, arising from differences in density between the current and surrounding water. They may be due to differences in temperature, salinity, or suspended sediment. Turbidity currents are caused by suspended sediment, and the resulting deposit is defined as a turbidite.
The concept of turbidites was first introduced to explain the origin of flysch sediments. Now, flysch is a term we don't often use today. It refers to thick sequences of interbedded sand and shale of deep-sea origin, as we see here in the Paleocene strata of Point San Pedro, California. The sands usually have erosional bases and are internally graded. That is, they fine upward in grain size. Also, the interbedded shales often contain deep marine fossils.
Turbidity currents move as surges with the transported sediment supported by fluid turbulence. Flow may be initiated by earthquakes, failure of oversteepened slopes, or by gradation from one of the other types of gravity flow. Turbidity currents flow like rivers in submarine canyons, initiating active erosion and cutting new canyons. Sediment is deposited both in the canyon and at the base of the canyon, where the currents spread out onto the basin floor, generally to form submarine fans. Deposition by turbidity currents can be very rapid, particularly at the base of relatively steep continental slopes, where most submarine canyons terminate. Deposition is accomplished by particle settling, with the coarsest material settling out first. A facies model for turbidites has been developed that consists of an upward fining sequence of textures and structures referred to as a Bauma sequence. The sequence consists of 5 divisions, designated from the base upwards as T sub A through T sub E. Starting from the base, the T sub A division is characterized by massive graded upward fining sand or gravelly sand with a sharp scour base. The T sub B division consists of a lower interval of parallel laminated sand. Some grading may be present, and the contact with the underlying interval is gradual. The T sub C interval is characterized by fine sand and silt that shows small current ripple bedding, often with wavy or convoluted laminations. The contact with the underlying interval of parallel laminations is rather sharp. The T sub D division is an interval of parallel laminations made up of very fine sand to silty clay with a sharp lower contact. The T sub E division is an interval of clay that tops the sequence. This interval may be divided into a T sub ET interval that represents terrigenous muds which have settled out in the waning states of turbidity deposition, and a T sub EP interval that is not a turbidite but rather represents deposition of pelagic marine muds. The complete Bauma sequence is seldom developed in any single turbidite, and the topmost part, bottom part, or both may be missing. In the proximal portions of a turbidite deposit, closer to the sediment source, all intervals are often deposited. As velocities progressively wane in the down current direction, the turbidity flow gives up its coarser fractions, leaving only the upper finer intervals to be deposited. Thus, within each depositional lobe, turbidites show a decrease in both grain size and bed thickness in a downcurrent direction. This hypothetical turbidite depositional lobe consists of a full Bauma sequence at the mouth of a submarine channel, and only the uppermost unit of the sequence at a location farthest from the source. The uppermost portions of a Bauma sequence are frequently scoured away by the channeling action of a subsequent depositional sequence. This may leave only the lowest-most units present in the proximal portion of a deposit. In more distal portions, where the lower units are often missing due to non-deposition, the upper units may also be missing because of erosion, leaving only the middle units.
We can generally recognize classical turbidites by certain characteristic features. Let's see how these features appear in turbidite exposures here on the coast of California.
Turbidites are characterized by a monotonous interbedding of sandstones and shales through many tens or hundreds of meters of section. Beds have flat tops and bottoms, with essentially no channeling or scouring. Here we see a number of fining upward cycles where basal sandstone beds grade upward from sharp and abrupt bases into finer sand, silt, and mud. Turbidity currents which form these deposits along with the other gravity flow mechanisms such as grain flow and debris flow are considered the most important agents in deepwater sand deposition. However, deposition from traction flow may also play a meaningful role, particularly in the deposition of sand within submarine channels. Research submersibles have observed and sampled at depths of over 600 meters large dune-like sand waves filling the floor of submarine canyons, as we see here in a canyon off George's Bank, offshore New England. These sand waves are composed of coarse to medium sand that is moderately to poorly sorted. They are asymmetric in form and attain heights of 3 meters and lengths of 15 meters between crests. Tidal currents, probably assisted by storm-generated currents, are thought responsible for transporting the sand from the shelf into this canyon and then reworking it on the canyon floor. Evidence for traction current deposition of ancient deep-sea sandstones has also been observed. Here we see trough cross-stratification produced by traction currents in late Cretaceous deep-sea channel sandstones deposited in the Delaware Basin of Texas and New Mexico. As we have seen, sand deposition in the deep-sea environment occurs most commonly as submarine fans. These features form at the base of continental slopes, where channels dump their sediment load in a manner analogous to a subaerial alluvial fan. A system of radiating channels, often flanked by levees, spreads out from the fan apex, with smooth, low-bait bodies forming seaward from the fan channel mouths. Generally, the coarsest sediment is deposited in the main feeder channel, in fan distributary channels, and in the proximal portion of the fan lobes. Finer grained sediment is deposited in interchannel regions and in the distal part of fan lobes. Several methods have been proposed to classify submarine fans. One such scheme identifies two end-member fan types, elongate fans and radial fans. Elongate submarine fans are the larger of the two types of fans, often being over 100 kilometers across. Elongate fans are also referred to as high-efficiency fans, delta-fed fans, and large deep-water ocean basin fans. Some geologists loosely refer to them as a muddy fan. Elongate fans develop mainly on passive continental margins, where basins are large and lower seafloor gradients exist. The fan is fed primarily from a single sediment source, usually from a major river system and its associated delta. Very fine sands and muds dominate, since sediment has generally traveled long distances from its source. A main feeder channel within a canyon breaks up into a number of prominent distributary channels. These channels, often with levees, have long valleys and extend over much of the fan. Sand bodies are formed as meandering channel deposits that are separated from each other by mud-rich interchannel and levee facies. Sandy fan lobes may develop at the terminus of the distributary channels. These lobes, essentially smooth and unchanneled, form sheet-like sands and have been likened to the stream mouth bars formed at the mouths of delta distributary channels.
There are many modern examples of the elongate fan type, and one of these, the Mississippi fan, has recently been subjected to extensive study. Now, a description of this fan can be found in your manual. Few examples of this type, however, are found in the rock record.
Our second major type of fan, radial submarine fans, are sand-rich deposits that typically form along active margins in restricted basins floored by continental crust. Note that we used this type of fan for our model when we first discussed submarine fans. Radial fans are relatively smaller than the elongate type, commonly being only a few kilometers across. Sediment is usually coarse-grained and well-sorted, with sand in equal or greater abundance than mud. The sediment, commonly derived from local rivers or from littoral drift on narrow shelves, is transported into the basin by a single feeder canyon or channel. The main channel generally divides into a limited distributary system to form a typical radial-shaped fan. Radial fans have been variously termed low-efficiency fans, restricted basin fans, and canyon-fed fans. The term sandy fan is also used by some geologists. Many modern examples of radial fans, from which this model by Normark was derived, are found along the western margin of North America. The upper fan contains a large levied valley that produces very coarse deposits 1 to 5 kilometers wide in meandering or braided shallow channels. The coarse deposits grade laterally into finer-grained, more regularly bedded levee sands and silts. The middle fan consists of a suprafan, recognized as a depositional bulge, that contains a coarsening and thickening upward sequence of sandy turbidites. The lower fan division is free of channels and coarse turbidites. It is nearly flat and often indistinguishable morphologically from the basin plane. Ancient analogs of radial fans are well preserved in the rock record. These fans provide for major hydrocarbon reserves in many regions of the world, such as Southern California and the North Sea. A model that best describes ancient as well as modern radial fans is one developed recently by Walker. On the left side of the model, Walker incorporated the salient features of Normark's model for modern fans with the characteristics proposed by Moody and others for many ancient fans. The inner fan consists of a single feeder channel. The midfan is made up of branching channels that feed the suprafan depositional lobe. The upper portion of the midfan is channeled, and the lower portion is smooth. The smooth outer fan grades into a basin plane. The right side of Walker's model contains the simplest possible terminology to describe the basics of almost all ancient and modern radial fans: a channeled fan, a non-channeled fan, and a basin plane. The use of such simple terminology as channeled and non-channeled is often preferred, particularly in cases where some doubt remains as to the assignment of arbitrary fan subdivisions. Furthermore, channelized sequences with their thinning and fining upward cycles and non-channelized prograding lobe turbidite sequences with their thickening and coarsening upward cycles can often be easily recognized, not only in outcrops, but also in the subsurface by cores and well logs. Several examples of ancient sand-rich radial fans have been reported from outcrop studies in California. One of these is the Upper Cretaceous Chatsworth Formation, located here in the Simi Hills on the Los Angeles-Ventura County line. The Chatsworth Formation consists primarily of arcosic sandstone that is subangular and immature. Thus, rapid sedimentation in a high-relief, tectonically active setting is indicated. Slope facies consist mainly of mudstone with thin interbeds of calcareous sandstone and limestone. Middle fan facies comprise more than 90% of the Chatsworth Formation. They consist of thick-bedded channel sandstones interbedded with thinner sequences of interchannel mudstone, siltstone, and sandstone. The channels are composed of medium to coarse-grained pebbly sandstone, poor to moderately sorted, and subangular. Rip-up clasts up to 3 meters in length are common. The beds are laterally discontinuous and composed of channel fills, often with pebbly scour bases. Individual channelized megasequences are up to 3 meters thick, and multi-story composite sequences are up to 200 meters thick and 1 kilometer wide. These megasequences are channelized at the base and downcut as much as 3 meters. In this case, we see the channel sequence downcutting into underlying bedded turbidites. Interchannel deposits form turbidite sequences of alternating thin beds of sandstone, siltstone, and mudstone that occur overlying and adjacent to channel deposits. The beds are up to several meters thick, laterally discontinuous, locally inclined, slump-folded, and display frequent wedge-outs characteristic of levee deposits. Outer fan facies consist of prograding sandstone and shale sequences that thicken and coarsen upward. Sandstones are generally non-channelized, laterally continuous, and flat-based. The sandstone beds average about 1 meter in thickness, and the sandstone-mudstone ratio is 1:1. These thickening and coarsening upward sequences are interpreted as representing outer fan depositional lobes deposited by turbidity currents. Many ancient deepwater sandstone deposits possess characteristics that do not fit the standard models for canyon-fed submarine fans. Basically, these non-fan systems are characterized by multiple or linear sediment sources that feed directly down a generally non-channelized or straight-gullied slope. The base of slope deposits generally lack the characteristic channelized upper and mid-fan and non-channelized lower fan subdivisions. These non-fan systems have been termed slope apron systems. An important example of an ancient slope apron deposit is the Upper Jurassic Braze system that developed adjacent to a major fault escarpment on the western margin of the South Viking Graben of the North Sea. Rapid erosion of the adjacent uplifted rock caused deposition of a thick sequence of generally coarse clastic sediments in a narrow zone about 5 kilometers wide that extends up to 20 kilometers along the fault margin. The sandstones and conglomerates that form the giant Bray oilfield reservoir interfinger basinward with organic shales of the Kimmeridge Formation. These shales provide the hydrocarbon source for the Bray field. The Bray system is divided into 3 main facies groups: mudstone, sandstone, and conglomerate. The mudstone group consists of laminated mudstone and siltstones or fine-grained sandstone. A variety of sedimentary structures indicate turbidity current deposition. The mudstones contain marine microfossils together with a mixed assemblage of marine and land flora and fauna. The sandstone group includes turbidity and associated flow deposits that range from thin 1 to 10 centimeter beds of sandstone up to massive beds of sandstones and pebbly sandstones over 40 centimeters thick. The conglomerate group consists of a variety of deposits, including breccias, pebbly sandstones, and pebbly mudstones that probably resulted from debris flow and other mass flow processes. These facies groups occur in an irregular slope-parallel arrangement, with base of fault scarp conglomerates interfingering downslope with pebbly sandstones, and sandstones that in turn interfinger basinward with progressively finer-grained mudstone assemblages. Here we see one of several variations of the slope apron model. This model, termed a fault-controlled submarine ramp, has been proposed to describe the Upper Jurassic Harild Formation of Greenland. Here, deep-water sandstones occur mainly as scours and gullies, deeply incised into black organic mudstones, with shallow shelf sands providing the sediment source. Large volumes of sand were deposited en masse in the scours and gullies, with liquid action of the sand probably responsible for some intrusion into the unconsolidated mudstone to form dikes and sills. The larger gully sandstone bodies are up to 50 meters thick, several hundred meters wide, and more than 5 kilometers long. The thick, extensive sand bodies of the Harild type are encased in impermeable organic-rich shale, and thus have the potential to become excellent petroleum reservoirs.
Let's now look at the 3 primary controls that influence submarine fan and associated deep-sea sand systems.
These controls are sediment type and supply, tectonic setting, and sea level variations. However, these controls are not independent of one another. For example, the amount and type of sediment supply, as well as local sea level fluctuations, are often determined by tectonic factors. In general, a single major source, such as a river or delta that supplies large amounts of sediment of mixed-size grades, often develops elongate fans. Coarser sediment, often with smaller sediment input, commonly develops radial-type fans. On mature passive margins, large elongate-type fans generally develop. On transform and convergent margins where rapid uplift, subsidence, or horizontal movement along fault zones takes place, short-term fans of the radial type usually form. On immature rifted margins and portions of marginal seas and transform margins, vertical tectonics dominate. Sediment is often dumped across steepened fault scarp slopes, and a slope apron system will tend to develop. Changes in global and local sea level have a major effect on deep marine sedimentation. During high stands of relative sea level, most sediment remains trapped in nearshore environments. Wider shelves predominate, and the amount of sediment transported across the shelf is reduced. Deep-water fans and associated systems therefore cease to develop or become relatively inactive. However, large elongate fans off major rivers may continue to grow, but at a reduced rate. Low stands of sea level result in narrow shelves and more rapid sedimentation, with sediments often funneled directly through canyons and fan valleys to deeper basins. Here we see the ages of tertiary and quaternary hydrocarbon-bearing submarine canyon and fan deposits from the Pleistocene reservoir sands of the Mississippi Canyon offshore Louisiana to the Paleocene reservoir sands of the Balder Field in the Norwegian North Sea. The ages of these deposits correspond closely with the ages of global sea level low stands displayed by this sea level curve.
Let's now take a look at facies associations in submarine fans. Submarine fan deposits have been classified into 7 different lithofacies, designated by the capital letters A through G. A description of these lithofacies and their distribution within a fan complex can be found in your manual. These lithofacies, however, can be easily confused with the subdivisions of the Balmer sequence, which also employs letter designations. Let's look at a more simplified description of facies associations on a typical submarine fan.
Classical turbidites are parallel-bedded, unchannelized sequences that occur on the smooth outer parts of suprafan lobes, the outer fan, and basin plane. These classical turbidites may also occur on channel margins or levees or in interchannel areas. Massive and pebbly sandstones occur in channelized fan environments, with the finer facies generally in the distributary channels, and coarse facies higher on the fan towards the inner fan channel and in the feeder channel. Conglomerates, if available from a source area, are found in the feeder channel, the inner fan channel, or as a basal lag in some distributary channels. A prograding fan can be expected to produce this overall coarsening and thickening upward sequence displayed by the Upper Cretaceous Pigeon Point Formation of California. Turbidites that are found in the smooth, unchanneled middle fan fringe as well as in the interchannel areas are overlain by the thinning and fining upward sequences of massive sandstone that occur in the middle portion of the fan. These massive sandstones are overlain by the organized conglomerates of the inner fan and feeder channel. Capping the sequence are slump-folded mudstones and mixed sandstones and conglomerates of the slope. Let's look at the exposures of some of these facies here in the Pigeon Point area. The middle fan environment is represented by thinning upward megacycles of channel sandstones. Each megacycle is composed of pebbly, coarse to medium-grained sandstone beds with scour bases 1/2 to 2 meters thick, corresponding to Balma T sub A and T sub B turbidites. Here, the upper medium-grained sandstone interval of a channel is truncated by a coarse-grained pebbly sandstone of a subsequent channel cycle. This cycle fines upward to medium-grained sandstone and is in turn overlain by the basal coarse-grained pebbly sand of the following channel cycle. Features characteristic of the channel margin and or levee environment are shown by this exposure of thin-bedded, fine-grained turbidites. These features include zones of slumping, small-scale disconformities, wedge-outs, and upturned sediment flaps. The slope environment is represented by these pebbly mudstones which are overlain by the organized conglomerates of the inner feeder channel. These feeder channel conglomerates are composed of beds about 1/2 to 1 meter thick, with each bed displaying a combination of features suggestive of both mass flow and traction flow processes. The pebbles and cobbles are mostly well-rounded, ranging in size from coarse sand to particles mostly 6 to 8 centimeters long. The clasts show well-developed imbrication with axes oriented parallel to channel flow. The instability of the slope environment has caused pronounced deformation of the mudstones as displayed by this slump-fold feature. In situ assemblages of macrofossils are rarely found in submarine fans and associated systems. Transported assemblages of macrofossils, however, are often found in the thick sandstones and conglomerates having been carried from shallow marine or even non-marine environments. Microfossils, found mainly in the finer-grained turbidite facies, may be good depth and age indicators, with some microfossils having been reworked from older strata. Thus, the presence of both shallow and deep-water faunas is often a diagnostic feature of submarine fans. Let's now look at how submarine fan facies appear on wireline logs and seismic sections. On gamma-ray and SP logs, channelized sequences display typical fining upward or blocky motifs, and prograding depositional lobes show characteristic coarsening upward profiles. Caution must be exercised, however, because deltaic facies may display similar profiles. For example, distributary channels fine upward like fan channels. Crevasse subdeltas, as well as deltaic distributary mouthbars, coarsen upward like fan lobes. Turbidites, however, can often be distinguished by a very nervous pattern, with the gamma-ray SP curve swinging back and forth erratically, reflecting thin interbeds of sand and shale from levee, interchannel, and lower fan deposition. On seismic sections, a canyon-fill deposit in transverse section typically appears as an onlap-fill seismic reflection configuration onlapping the canyon walls. Local sand-prone areas are characterized by high-amplitude, internally moundy, discontinuous reflections. The seismic signature of the typical lower fan facies includes overall mound shape, convex upward reflection patterns with bidirectional downlap, and commonly high-amplitude reflections.
Let's look for a moment at how the concepts of sequence stratigraphy may be applied to the prediction of deep-sea depositional environments and lithofacies.
Here we see the fundamental unit of sequence stratigraphy, a sequence which is a body of genetically related strata bounded by unconformities and their correlative conformities. A depositional system is a body of genetically related sediments, one or more of which make up a depositional sequence. Contemporaneous depositional systems may in turn be linked into units called systems tracts. Deepwater reservoir quality sands are usually deposited in low-stand systems tracts. When some or all of the shelf is subaerially exposed, streams downcut into the shelf, and sediment is deposited on the slope and the basin floor as point-sourced, relatively sand-rich low-stand fans. As sea level slowly rises after the deposition of the low-stand fan, downcutting of the canyon slows, and levied channel deposits along with overbank turbidite deposits form beyond the canyon mouth. These deposits are sometimes referred to as a slope fan. They are generally finer grained than low-stand fans, with sand usually restricted to the channels. As we mentioned, deep-sea sands are often highly productive oil and gas reservoirs. In favorable environments, thin, laterally extensive turbidite beds of outer fan facies tend to interfinger with surrounding organic-rich muds. Ideal conduits are thus provided through which hydrocarbons can migrate up-dip into sandy depositional lobes and channels of the fan or slope apron deposit. Migration directly from source to reservoir may take place where source beds blanket the sandy depositional lobes, as well as where sand-filled channels or channel levee complexes are encased in source muds. In general, channel and channelized lobe sands have better porosities and permeabilities than the turbidite sands occurring in interchannel areas or in the more distal regions of depositional lobes. Consequently, they tend to form the best petroleum reservoirs. Now, let's look at some examples of oil and gas production from deep-water sands. A system of submarine canyons containing gas-productive Oligocene hackberry sands is located in the vicinity of the Texas-Louisiana border. The canyons extend down the paleoslope and incise into underlying shales. A cross-section of the North Sabine Lake field shows that many small lenses have coalesced to form a single large reservoir with a gas-water contact here. Other small sand lenses not connected to the main reservoir complex have produced only small amounts of hydrocarbons.
Major oil and gas production has been obtained worldwide from deep-water sandstones deposited in submarine fans. Let's look at two examples.
Over 400 million barrels of oil have been produced in 15 fields from the Upper Miocene Stevens Sandstone, located on the Bakersfield Arch of the southern San Joaquin Valley, California. The Stevens Sandstone encompasses more than 1,200 meters of interbedded sand and shale. During 4 cycles of turbidite deposition, fans issued simultaneously from the Rosedale and Fruitdale canyons. Some oil production comes from these proximal canyon-filled sands of the feeder canyons. Most of the oil production, however, comes from the sandy channelized mid-fan facies of submarine fans. Oil accumulations in these mid-fan facies occur as the result of 2 distinct mechanisms: growth faulting and differential compaction. In the case of growth faulting, entrapment results from the stratigraphic discontinuity created between the upthrown and downthrown blocks. Another type of trap is associated with the downthrown rollover anticlines. The second major trapping mechanism in mid-fan facies is created by differential compaction. Compaction of interchannel shales creates shallow synclines in interchannel regions, leaving the sandy distributary channel areas as structural highs. Because of alternate stacking of distributary channels, a broad productive anticline often occurs over an underlying non-productive syncline. Conversely, a non-productive syncline may occur over a productive anticline. Some oil occurs in the lateral margin fan facies of the Stevens sand as a result of wedging out of the sheet-like turbidite facies against a paleobathymetric high. However, prolific oil production is obtained from fractured shales of the distal margin facies, where local flexures have created fracture systems up-dip from mid-fan sandstone reservoirs. The Eocene Frigg field in the Viking Graben of the North Sea contains over 7 trillion cubic feet of recoverable gas. The Frigg feature is one of several submarine fans in the Viking Graben that provide giant oil and gas accumulations. A vertical stacking of sandy turbidite channel lobes occurred in the Frigg fan, with channel lobes deposited above the compacted shaly section on the flank of underlying thick sandy deposits. Compaction anticlines were created, providing traps for hydrocarbon accumulation similar to the Stevens sand in California.
We have seen that deep-sea sands have yielded significant oil and gas production in many parts of the world. Now, please consult your manual for a more detailed description of the fields we have just looked at, along with descriptions of other fields producing from deep-water sands. Now, this concludes our series on reservoir sandstone environments. Good luck.